Hello and welcome to this presentation on stacks and queues. It turns out that a lot of programming algorithms and applications can be made simpler if you use certain types of data structures. Two popular data structures that are commonly used to help implement certain algorithms are called stacks and queues. And the good news is that the stacks and queues are just special types of lists. They're lists that have insertions and removals done in a specific way. A stack is similar to a stack of plates or trays like you might see in a cafeteria. The clean trays or plates are pushed on top of the stack, and then when a diner or customer goes to get a plate or a tray, they also remove it from the top of the stack. So a stack is a special type of list where insertions and removals are done from the same end. And so sometimes they call this a LIFO, or last in, first out. So the last item that's put in the stack is the first item that's removed from the stack. So again, a stack is just a list where insertions and removals are done from the same end. These two operations on stacks, the insertion and removals, are commonly called push and pop. And so here we can see we have a stack and it has the letters A, B, C, D in it, and a push operation would push or put E onto the top of the stack, and then this would be the new result of the stack. And here, the reverse of that, removal or the pop operation, is we take the top item and remove it so it gets popped off the stack. In some implementations, the pop operation will return the value that gets removed. In C++'s standard template library, it doesn't do that. So we have another operation before, sometimes before we do a removal or pop the stack, we want to actually get the value of the thing on top of the stack, and sometimes it's referred to as peek, or in the standard template library they call that top. So top would get you a copy of the value on top of the stack, and then you can pop it, actually remove it. It's also not uncommon for stacks and queues to have some additional typical list operations, like getting the size and determining whether the stack or queue is empty and clearing it altogether. A queue, again, is a special type of list, and you can think of it as a line of customers waiting to be served. So here we have a line of kids waiting to get ice cream, and here we have a line of people maybe applying for a job or something. When a customer or someone gets in line or gets in the queue, they get in the back, and when a customer is served, they're served from the front of the queue. So a queue is a list where insertions and removals are done at opposite ends. So we think of insertions being done at the back of the queue and removals being done at the front of the queue. And so they call queues FIFO, or first in, first out. So the first thing that was added to the queue is going to be the first thing that's taken out of the queue. The queue operations have kind of odd names maybe. They call it enqueue to do an insertion or add, and a dequeue to remove it. So here's an example of a queue. We have the front of the queue with A, B, C, and we're going to enqueue the letter D, and now the new queue has A, B, C, D in it. The removal then is done at the front of the queue. So the queue with A, B, C, D, when we do a dequeue, the A gets removed, and now the queue just has B, C, D in it. And again, you can see it's just a list with insertions and removals being done at opposite ends. Here's an example of a stack. You can see the top of the stack here, we would push a 5, and then in the next step we might push a 2 on top of the stack. And then in the next step we would push a 3, so now we have 3, 2, 5, and then if we popped the 3, then we'd only have 2, 5, and then here we push a 7, and here we push a 14 on top of the stack. And those are the steps that would cause this to happen. One implementation of a stack would be to use an array or a dynamic array, and we can just conceptually think of the array as turned upside down, so that the bottom one here is at index 0, and then this would be index 1 and index 2 and index 3. Instead of doing a push and pop always at index 0, that would be a little bit more challenging, because if you had a stack of, say, 5 things and you wanted to push and insert it at the beginning of the array or at index 0, you'd have to copy all the current contents of the array down 1 to make room at index 0. And that's a little bit less efficient. So if we're going to use an array for a stack implementation, then you'd want to do the push at the other end, the higher index, or the current size, as we've seen in our dynamic array insertions. Here's the queue, and you can see that we enqueue 4, so 4 goes in the front of the queue, and then we enqueue, 4 actually goes in the back of the queue, which for an empty queue is the same as the front. And then we enqueue 2, and that goes in the back, and then 5, that goes in the back, and then we dequeue, which removes the 4, so now we just have 2 and 5. We enqueue a 3, it goes in the back. We enqueue a 7, it goes in the back. We do another dequeue operation, and the 2 gets removed, and so the result of all these is a queue with 5, 3, 7 in it. One real common application of a stack, we'll look at a couple of applications, but one common application of a stack is to reverse items in a list. If we go back and look at the stack example, let's just say we have a list of 5, 2, 7, and 4. If we push those values in the queue in that order, 5, 2, 7, and 14, and then pop them out and print them, we would get 14, 7, 2, and 5. So one common application of a stack is to reverse items in a list, or do things in reverse. Let's look at a little bit of code. The lab for this week has some sample stack code, and if we look at it, we can see that it's implemented as a stack of characters that are stored in a static array. And so we have a maximum size for this stack of 10, and we're keeping a location of the top of the stack as an index or integer. And we have an operation to push a character onto the top of the stack, to pop or remove a character, and to peek at or get the value at the top of the stack. So here's the push operation. Notice that the constructor sets the top to 0, so that's the first place that we're going to push when we go to add an element to the stack. So if we push an element to the stack, a character to the stack, we're going to put it initially at lists of 0, and then increment top, so now top will be at 1. To pop an item off the stack, we simply decrement top. So it doesn't technically remove it from the array, but it moves what we think of as the top of the array down 1, so that we don't care about the value that was previously on top of the stack. And then to peek at the stack, we would just return the value at top minus 1. And if you think about it, there's a potential problem here. What if the stack is empty? What if we try to peek at an empty stack? That's a potential problem, and that's part of your assignment to find a way to deal with that this week. So let's see maybe if we could use this stack to do a reverse operation. So what I'm going to do is create a program that wants to try to reverse, say, your name or an item in reverse the items in a list. So I've got some code here that's going to read in a string. And then print out the name in reverse. So here we prompt the user to enter in a name and then read in that name and then print out your name reversed is. And we haven't actually done the reverse part, so if we run it like this, we'll just see the name in the order. So here I've got enter your name, I type in Chris, and it prints out your reverse name is, and we didn't set it to anything. Reverse name was not set to anything, so we don't get any output. So we don't even get any output yet. What we'd like to do is be able to print out this name in reverse. So what I will do is add this stack code to my project, so I can add existing items and go find where I put this simple stack class code. And sometimes it's useful before we start using something just to try to compile just this module and see if it has any errors in it. So I can just go to the build menu, or I can right click and compile just this stack.cpp file. It doesn't build the entire program, it just confirms that there are no errors in that stack.cpp module. So then in the main, I could include stack.h, and then I could declare a stack. Let's see what the name of it was. I must have spelled it wrong. No, there it is. Let's see. Oh, so the problem here then is it can't find stack.h because it's actually in a different folder. So let me see if I can locate it. The folder structure that I have in this CEIS 295 directory is, I think the current project that I'm running is pointer test, which is here, and then the stack code is up here in a simple stack class. So what that means is from inside this folder I have to go up one directory and then down into this one. So, and unfortunately there's spaces here in this file name, so I'm not sure how easy this will be to do. Let me try this and see how this might work. So that goes up a directory, and then there's a simple stack class, and then stack.h. So okay, so that seems to work out all right then. So now I've got a character stack, and then I can do a range-based for loop for each character in the name string. Just push it into the stack. So I'm just looping through all the characters in the name and pushing the characters into the stack. And then I can do another loop while the stack is not empty. So I can either do not empty or get size greater than 0. So as long as the stack is not empty, then I can take the reversed name and concatenate the thing on top of the stack. So I'm taking the character that's on top of the stack and concatenating it or adding it onto the string reverse name. And reverse name initially starts out as an empty string. And then after I've done that, then I'll actually remove that top item of the stack or pop the stack. And so we're taking out all the characters in the stack from top to bottom, and they'll be in reversed order, and that should reverse the name for us. So if we build and run this, it's asking for a name, and I'll type in William, and I've got some type of error. That's interesting. So let's see what's wrong with that. That might be a problem. That's interesting. So let's use the debugger and see if we can figure out why this isn't working. Okay, so I'm going to put a breakpoint here, and I'm going to run the code in the debugger, start debugging, and I get the prompt where it's asking me for the name, so I'll do William again. I don't think William's longer than 10 characters, so that shouldn't be the problem. And then for each character in name William, I want to push it into the stack. And so the character stack, we can see here the list has a bunch of uninitialized characters in it, and the top of the stack is at 0. So when I do a push, I get the W, and then the next one I get the I, and then the next one I get the L. Maybe tough to see as a small font here. And I get another L, and an I, and an A, and the M, and that should be it. Okay, so now we're going to try to get the reversed name. So character stack get size, and we're going to peek at the top of the stack and add it to reverse name. So reverse name is empty, and now reverse name has the M, which is the last character. So that makes sense. And we pop off the stack, and now the top of the stack is at 6. So 0, 1, 2, 3, 4, 5, 6. So the 6 is still at M and M. So I wonder if the pop operation for the stack is working properly. It should be minus minus. Did I count wrong? Let's see. So it's still showing me, oh, okay, so it's showing me that the top of the stack is at 6, but after I pop the M off the stack, it should have been at okay, so what they're doing in this stack implementation is their top is the location where you would add the next thing. So when they do the peak, they're actually peaking at top minus 1. Okay. So now top minus 1 would be the A. So if we run through this, another iteration of this loop, the stack size, okay. So here's where I have an error in the code. The get size method that they have for this stack class is not actually returning the number of things that are in the stack, it's returning the maximum size that the stack can hold. And so in my algorithm, I should have used the isEmpty method. So that's what's wrong with the... So this get size is actually getting the capacity of the stack and not the actual size or the number of characters in the stack, because the capacity of that stack is 10. So I had an infinite loop here where this is always going to return 10, and it's just going to keep adding on to this string until it takes up too much memory. Okay, so I need to change the algorithm, so I'll stop debugging. And I need to change this while the stack is not empty to be something like this. Is empty not. So as long as the stack is not empty, get the value on top of the stack, add it to the reverse name, and then pop that value off the top of the stack. So now if we run this, tap in Margaret, we get the reverse name of Teragram. And so this is an example of how to apply the stack to reverse items in a list. And one other thing I'd like to show you is that the underlying implementation of the stack doesn't matter. So in this case, the underlying implementation of the stack was a static array. But it turns out that the STL C++ standard template library, in addition to having a vector class that's like a dynamic array or linked list, also has a stack class. And so I can replace the stack that's used in the example code for week 3 with the character stack from the standard template library. And the only thing that we need to change then is the name of the method calls. The standard template library stack methods are a little bit different than what we have. So there's, I believe it's just called empty, to test to see if the stack is empty. And instead of peak, they call it top. And we run this and it should do the exact same thing. Okay, Aseret or whatever was reversed of Teresa. So the important thing here is that a lot of times you can use data structures without really understanding how they're implemented, the underlying implementation. So for example, the STL stack, I'm not sure if it's implemented as a dynamic array or a linked list. I'd have to look in the documentation to see. But I can effectively use this STL stack class to solve a problem without knowing the details of the underlying implementation. Where you'd want to look up those details in the documentation is when you're interested in performance and you want to choose the data structure that meets the requirements of the application best. So let me know if you have any questions on this presentation on stacks and queues.